of our design was dependent on requirements and materials. We also searched some documents and decided our initial design. First of all, we can see the front wheel. One area that deserves attention is our base, where we choose to use A4 paper and sand. We put paper first and then we added sand on the paper, pressed it down so that the high-density sand becomes a solid base. Also, it not only reduced the material usage but also the cost. Next, we noticed that the distance between the two bases was 450 millimeters, but according to the given size of the plank, we need to divide the bridge into two parts for joint, which means that the middle part of our bridge needs to be glued together. Therefore, in order to increase the strength of the bridge, we add some sidebars inside the bridge and connect the piece of wood plank with string below the joint. As you can see from the section A to A, we even added some sidebars which parallel to the bridge to make the joint strong. From the top wheel, a 150mm wooden door was necessary because it allowed the bridge undergo a small shear force, which can make sure the bridge was safe. In a word, all of our designs were aimed to make our bridge safer.
We had to make fundamental changes to our design after receiving feedback during the build session. Our original model had a deck thickness of 55mm when the maximum allowed by the brief was 30. I amended my original laser cutter model by reducing the beams to a thickness of 22mm. This was as large as was allowable, as the polystyrene had been hand cut to a depth of 8mm. Unfortunately, our design revolved around maximising the deck thickness after learning about its effect on stress and moment in Civ 1200. This meant our revised design was far weaker than the original proposal. Thankfully, after reducing the width of the beams, plenty of plywood was freed up, allowing me to add more crossbeams to the design, taking us from 6 to 10. I did this in the hope of more evenly distributing the load and reducing the stress on our now weaker frame. While I don't believe it took us back to the strength of the initial design, I think it allowed us to compensate somewhat and was the best I could do without altering our whole design. Additionally, as our final design used less material, our final mass was lower, allowing us to reduce the overall project cost. On top of changes to the frame, we decided to attach the superstructure to the bridge deck using sellotape. This prevented the dowels from splaying outwards under load and causing collapse by providing resistive tensile forces.
Let's go section 3, see how and why our bridge failed. When we put 4 kg mass on the bridge, the joint, start out position, and the bottom board didn't share much pressure. But the other side is working good. This shows that the bearing of the bridge is not uniform, and the tape we wrap on the front side is not very strong, and that makes the structure change. When we start to add weight to the bridge, the deck began to tilt.
3, everyone's running off the bridge.
Yeah, this wasn't here.
And we can see from here the joint is out of position more and more.
It's just that thing's getting...
The right side of paper abutment is not horizontal. The sand flows out from the gap and accelerates the inclination of the deck. And the beams begin to shift. We can see from here the perspex box supports a lot of mass. And what happened next?
Do we feel this is now?
Yeah, it's fail.
If we were to do this again, there are improvements that we would make to build a better bridge. The middle of the bridge deck failed first, therefore the joint in the middle will need to be improved. For our bridge, the joint in the middle between the two pieces of plywood at the sides were connected together by sellotape, and the connection became loose when the load is applied because of the lack of support and the properties of the tape. The plywood underneath the superstructure will need to be redesigned to support the plywood beams at the sides properly to avoid it from bending with only a small amount of load. In the test, one side of the beams were properly supported and remain intact even after test. Therefore, if we make the plywood underneath wider or by fixing it in place with some tape, we can significantly reduce the deflection in the load test, especially during the early stage. Filing the end of the dowels to the right angle will help to produce a more rigid connection between them to allow more load on the bridge before it ultimately fails.